Jockman's here to give you some good old-fashioned Day 52 AP homework answers. We're going to start with number 1. An amusement park ride has a large cylinder that rotates around a central axis. And you stand against the inner wall. At some speed, the floor drops, and instead of falling, you stay in place. Question A. Draw and label all the forces on it. Okay, we know for sure there's weight happening. Now, you know for a fact that if this thing did not have walls, somehow you'd end up going further out and spinning outwards on a tangent velocity. So the walls are keeping you in place, which means there's a normal force, inward. But wait, you're not actually going down. Something's got to keep you from dropping. The force that's keeping you from dropping is actually the friction. And it's keeping you locked in place. So that's letter A. Letter B says, explain what conditions are needed to keep the passengers from sliding down. Okay, so in order for the passengers to no longer slide, friction's got to be more than weight. That's it. But if you don't mind, I'm going to go a little more in detail with this. I'm going to say that friction is mu times the normal force, then we know. As long as there's more friction, you will not keep moving down. You won't go up, but you'll keep from dropping. Now, if you're not moving, is this the static or kinetic coefficient of friction? Exactly right, static. But remember, normal force is the only force towards the center of the cylinder. So the normal force is the centripetal as well. Again, I know this because the imbalance is the normal force. So I can say that mu times the normal force, which in this case is mv squared over r, is more than the weight. I'm going to put mg in there. Do you see what cancels out? I do. When I'm like, Jockman's, I don't get it. It's the same statement as up here. It definitely is. But I'm going to show you in part C why this is important. So to summarize part B, the first is got to be more than the weight. Friction is mu times normal force. Since the normal force is the amount of imbalance, because it's the only force going in, the normal force is the centripetal imbalance, mv squared over r. Mass on both sides cancels out. Letter C is, excuse me, what conditions are there for a person that's twice as heavy as a kid? Well, you can see the mass actually canceled out. So they're going to have the exact same conditions. And that's why this ride works. It doesn't matter if you're a small kid or you're an adult. Since the mass drops out, and the only thing you need to do in order to go around and stick on the wall is to have the friction times the velocity of rotating squared all over the radius be more than the gravity. And that, my friends, is number 1. Let's go on to number 2. For number 2, it's actually not too bad. We're going to have a wrench with a bolt. And we have to find the torque produced. This one's not too hard in terms of its idea. The force is perpendicular, and this distance is 0.2 meters. With a force of 20 newtons, we know the torque produced by the end is the force times the radius perpendicular. Doing that, we get a torque of 4 Newton meters, which I believe is answer C. Not too tough. It's about time to get into some craziness, however. So can you please join me for number 3 in a moment? And now it's time to go over number 3, and also number 4 and number 5. They're all kind of the same idea. It's this new angular stuff I just taught you in class. So number 3 says, what is the angular speed? Our goal is to find this omega. A record that goes at 33 1/3 revolutions per minute. This is straight up dimensional analysis. We're going to convert this 33 1/3 revolutions per minute to the angular speed, which is radians per second. Let's start with the phrase revolutions. Is that pink okay? My director says yes. Thank you, Emma Javelin. One revolution is one tool. Yeah, that's great. One turn of the circle. How many radians is one turn of a circle? You got it. 2 pi radians. I now have the radians part. I want to get seconds. Minutes on the bottom. 1 minute is 60 seconds. So doing it all together, I'm going to get 33.3 times 2 pi radians all over 60 seconds. And you get around 3.48 radians per second is my angular velocity. Congratulations. The purpose of this was to make sure you now know about revolutions and radians. Number 4 says, an object rotates at an angular velocity of 126 radians per second. What angle in degrees will it be displaced after 6 seconds? So think, if it starts here, and after 1 rotation, it'll be back where it started. It has not displaced any amount of degrees. If it ends up down here, that's a displacement of 180 degrees. So this is going to be kind of unique. I'm going to guide you through it. The first thing I would personally do is I would find how many revolutions it did. Velocity is displacement over time. Angular velocity is angular displacement over time. This is 126. The time is 6 seconds. I'm going to get the angular displacement to be, I believe, 756 radians. Cool. I'm now going to find how many revolutions it is. And I'm going to do some cool little logic, which I want you to follow. Well, 1 revolution is 2 pi radians. So this ends up with, I believe, where am I? 120.32 revolutions. It's not my answer, but I'm circling it. How many revolutions? Well, that's a harder question. Let me try that again. If I want to find how much it displaced by, 1 full rotation is 1 revolution. So in other words, this really got displaced only 0.32 revolutions. We don't care when it ran 120 times. All we care about is how much it ended from its start, which is 0.32. 0.32 revolutions times 1 revolution is 360 degrees. And I get 115.5 degrees. Good. That's how much it displaced over the entire time. Make sense? Hope so. Now let's talk about number 5. A flywheel, I don't know what that is actually, of radius 1 is spinning at a constant angular speed of 2 radians per second. Find the centripetal acceleration. As I taught you in class, centripetal acceleration is v squared over r. And I also taught you that velocity is radius times the angular velocity. I'm going to plug this in for v. We derived this in class, so it's good to have on video anyway. By plugging in r mega in for v, I can now solve the centripetal acceleration in terms of centripetal angular velocity. And it's radius times mega squared. Okay, the radius is 1. The constant velocity of 2 squared, it gives you 4. And 4, which is letter C, is the correct centripetal acceleration in meters per second squared. It's been a lovely time. Thank you for your hard work. I look forward to seeing you in class. Goodbye.